So we're rolling.
Yeah, we're rolling. How's it going, Kat? Good to see you.
Give me a hug.
How are you doing today?
Good. It's a little rainy, but otherwise it's good.
A little rainy in San Francisco. Yeah, it's like it was raining cats and dogs outside, but it's chilled out lately.
The wind was shaking the house so much that I thought we were having an earthquake.
An earthquake, yeah.
Yeah, it was earthquake time.
Yeah, sometimes those things come through the city, but it's nice to have. It's sunny now, so I guess it's over.
Yeah.
So,
we made it.
Thanks for inviting me by your house. And, today I just wanted to talk a little bit about ROS. I mean, you're the developer. I mean, you run ROS's developer advocate ecosystem?
Yeah.
Yeah, tell me about that.
Well, so ROS is probably the oldest, largest open source framework for robotics. It's been around for close to 20 years now.
Mm-hmm.
We're on our second version, and we're on our 10th or 11th release. Kilted will be K is 11, right? So it'll be our 11th ROS 2 release is in May of this year.
Mm-hmm.
And ROS is used across the globe. We have ROS users on every continent. I know we have one on Antarctica now. We have...
How did you learn about that, actually?
How did I learn about that? There was a research group that uses ClearPath robots as a platform to, I think what they were doing is they were using the robots to go send sensors out into like different spots in Antarctica and collect data.
Mm-hmm.
And they published a paper on it. We're like, oh, so ROS is in Antarctica. Worldwide. Let's see. I just checked. I want to say we have somewhere on the order of like 1,300 companies that we know about using ROS.
Mm-hmm.
It's probably much more than that. These are just the ones that we know. Like somebody will send us like a job listing that says ROS, or they'll sponsor ROSCon, or that kind of thing. That's how we keep track of those numbers. It's probably much larger than that. And that's, people are like, oh, ROS is just used by academics. Yeah, it's used by academics, but it's also used by, Fortune 50 companies. It's used by little tiny companies. It's used for R&D companies. It's used by manufacturing companies. It's used for, people building, things kind of at the edge of R&D where it's like, we're doing the research and development to go build a robot that goes and dives down around oil derricks to inspect pipelines, or we're using ROS to go build robots that use lasers to burn up weeds in a field of corn, or like it's just everywhere. It's all robotics verticals. And really at the end of the day, what it is it's just standard library of robotic functions. It's the design patterns that we as software engineers have realized work and are tested and are usable, and they've been put through the ringer and they actually work. And we've all decided that like this is how you kind of architect robots.
Yeah, and ROS, like fundamentally, you got the message passing layer that allows you to create a bunch of separate applications. Mm-hmm. And each of these applications can then publish and subscribe to different topics.
Yeah.
Right? And so I can make one application that publishes a topic, and then another engineer can make another application that subscribes to those topics. And this allows me to build a network of different functions where each engineer could like control a different piece of software that has one particular job, and then they just publish what they need to talk to other pieces of the software with, right?
Yeah, that's roughly it, right? So there's this thing we call the ROS middleware layer,
mm-hmm.
which is fundamentally an abstraction layer. People will say it's DDS. Well, it's not just DDS now, but you can use Xeno, you can use a bunch of different protocols, at least for ROS 2. ROS 1 was all bespoke and we wrote it once and everyone used it.
Mm-hmm.
ROS 2, we've made it so that you can yank out the transport protocol and put in what you want.
Mm-hmm.
It's actually, we've had a lot of work in marine robotics lately. So there's a group that just published some work and a new RMW layer for communications, like subsurface communication. So, when you're underwater, you're usually, the way you transmit messages, wireless doesn't always work all that well. So you have to use like sonar, or, I know nothing about this, but I now know that there's this layer that you can plug in. And if you want to do communications under subsea communications, we can do it in ROS. But ROS is fairly modular like that, mm-hmm. so that you can yank out that thing and use another thing that somebody else can write, say a navigation layer or an inverse kinematic layer for your robot, and you can just pick it up and use it. It's a lot like Python like that, where you just have packages.
Yeah, and ROS 1.0, you had this launch file system that really helped organize how programs got parameters and were launched and setting up topics. I remember using that back at work. And then also, I think the biggest thing though was the recording layer that would then grab all the topics.
The ROS bag, yeah.
Yeah, allow you to like record the state of the thing. So like you were basically recording the brain activity of a robot, more or less, right?
Yeah, it was. So, like people think like logging, right? And we do have logging. Logging is a distinct and separate thing, right? Where you say, oh, log this thing, I started this thing failed, critical error. But then in a robot, right, you have all this data moving across the network, right? You have sensors from your LiDAR, you have like, encoder clicks from your wheels. You have all these different bits of data and they're all moving through the system and you're making decisions based on that data, and you really need to be able to record it and play it back to debug things. Like that's the only way you're going to be able to debug a robot. And being able to like run one command, ROS do, ROS bag, blah, 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 and just drop it into a file, and then being able to like upload that file to Google Drive or to the cloud and send it to somebody else to look at is super duper handy. And that's one of those free and open source tools that you get when you use ROS.
Yeah. And so you guys, I know that there's a big thing of going from ROS 1 to ROS 2, and it's probably still happening, that transition.
It's 80% done.
Yeah. It's kind of like the Python 2 to Python 3 transition. Whereas just getting all the people to go from Python 2 to Python 3 is going to take forever, but it's getting done.
As of December or maybe October, I pulled the numbers. These off our servers, it's at 80%. I don't think it'll ever be 100%. There are still people using Python 2.7 in 2025. Like, there's nothing you can do, right? But like, we're close. Like, no one should be starting a new project with ROS 1. No one, I think, is. There's some people who might hold on to it for a couple more years because they have different priorities, and that's fine. Nothing's going to explode, but I think we're over the hump, and ROS 2's ready to go. It's tried, it's tested. People are like, "Has it ever been used in production?" They're like, "Yes." Do you have a vacuum at home? It's used in almost all the robotic vacuums. ROS 2 is ready to go.
Yeah,
it's used in production.
What was the big difference between ROS 1 and ROS 2? Because both of them have the same high-level features we just talked about, but you guys changed a lot of stuff, hence the version bump, right?
Yeah, there was some, there's the first problem of, right, when you have a lot of people relying on you, and you want to make breaking changes, right, you necessarily have to do a big jump, a big number jump. Like, you want to tell people, like, look, we're doing this change. Things aren't going to work perfectly, because usually between most ROS distros, like, the changes are pretty minor. Like, I hear a lot of people like, "Oh, I'm so scared of changing." By and large, most of those things are like changing a few lines of a file, recompiling, running your test, fixing 2 or 3 dependency related issues. But between big versions, that's a lot harder. And the big differences in ROS 2 between ROS 1 is, that middleware layer was a big one, right? Because in ROS 1, we said, okay, we're going to write all of this. We're going to write it one way. And that way was really, really good if you are a graduate student and just want to get started and get going and have everything work. That layer was probably not the best solution if I am, say, an AMR vendor in a huge facility with tens of thousands of robots. Or, like that subsurface example I gave earlier, right? Like that layer, you needed the flexibility to yank that layer out and put another one in to deal with these different applications. So that was a big one, and then there was just things that we had found over the years that needed to be changed, things we could have done better. Like, so like one of the paradigms that's changed in ROS 2 is you have this notion of life cycle nodes. Basically, we found everyone was saying, well, my single tiny ROS program needs to have a sort of start state and end state and have communications about how it spins up and spins down. That was a big one. Some changes in how, like, give people more flexibility to pick how things are executed within their nodes. Like, how do you do different priority queues? Like, because different people have different ways of doing things. So you need to change how you can handle priority queues within your ROS node. There's a laundry list of stuff like that, but a lot of it was just improvements, breaking changes that we wanted to do to improve the system for these like critical sort of production-oriented systems.
I see. Yeah, I mean, and one of the new features of ROS 2.0 is that you can really run, because the middleware is shifted out, you can now run it on all types of systems, correct? Like, you can have different operating systems communicating to each other using ROS. that aren't just desktop OSs, but you can also have microcontrollers and various other things talking and using the same protocol, right?
Yeah, so there's a group that does. I think a lot of this is led by our European colleagues.
Mm-hmm.
So there's micro ROS, right, which is essentially, can we build a subset of like the ROS API that can run on embedded microcontrollers, right? So you have a little tiny system, and say it's running an encoder or running. I'm hacking something together. I have like I want to have a board that has like 5 servos on it. And then I want to connect that board with 5 servos on it to a bigger robotic system, like say a Raspberry Pi, right? That big Raspberry Pi might run ROS 2. The little tiny, I don't know, it'd be like ESP32 board, right? This ESP32 board with 4 servos on it. It connects to this big thing. This little tiny board over here may run what we call micro ROS.
Yeah.
And so you get like most of the functionality, and you spin up the systems, or you spin up that smaller board, and the bigger ROS system sees, oh, I can call these 4 API calls in the way I'm familiar with, right? Or I can get my data from that smaller board in a way I'm familiar with.
Yeah. But that takes care of a lot of the connectivity problems, I think. And that also leads us into what I wanted to talk to you about today, which is, so we have a new OpenMV Cam that I wanted to share with the ROS community, actually. And so this is the OpenMV Cam AE3. It is a 1-inch by 1-inch camera that has the ability to run neural networks on board, draws about 1/4 of a watt of power to run YOLO, for example, at 30 frames a second. And it has, USB, I2C, and UART that allow it to pretty much interface with, a computer. And so this thing, it's going to be possible for people to build applications that leverage this, and they can connect it to ROS. Want me to open it up?
Yeah. Wait, and so wait, tell me a little bit. What's this sensor next to the lens right here on the left?
That is a time of flight sensor. So we've got an 8x8 time of flight sensor on this guy.
So it solves the depth problem, right? The depth.
Yeah. People always ask us on the OpenMV forums, like, what's the distance object is from the camera? And I'm like, trick question. Cameras don't measure distance. So.
They can't.
people always want an answer for that. I'm like, there's no answer. You can guesstimate by just looking at the size of an object, and you don't
know if it's a dollhouse close up or if it's a real house far away, but like the same problem.
No, so we got 5 sensors on board this guy. There's a 1 megapixel global shutter color camera that can run at about 120 FPS full res and 240 FPS in VGA. You won't quite get those speeds on board this guy just because it can't process that amount of data that quickly. But still, the camera is capable of doing that. But you do actually hit 240 FPS at 320 by 240, though. So very, very high speed. Looks like the little bit of earthquake happening from that.
That might actually be an earthquake.
Oh, a real one. Oh, wow. I can feel it. Yeah.
Honey, will you check the earthquake thing? He's got his headphones on.
Oh, yeah, no, it's okay. Whatever. Anyway. Welcome to San Francisco. All right, anyway, back to the movie. We got going on here. Also, that's the camera. But the best part is it's color global shutter. So triggerable, meaning that if you wanted to build like a pick and place machine or whatever that, triggers it on something happening, you can actually do that. Then behind the camera, we actually co-located a IMU. So it's got an accelerometer and gyroscope square behind the camera, exact center pixel. Oh,
so it's all lined up. You don't have to do all this weird translation between the two. That's nice. That's a nice placement.
Yeah, it's a nice placement.
You get to choose where you place stuff, and that's the correct place to put that. That's cool.
No, and then also what's
the frequency?
That's on SPI. So you're going to be able to actually push that up to the I think it's the standard IMU part. I don't know the exact numbers off the top of my head, but we have the fastest interface available for it, so you'll be able to get it up beyond a kilohertz at least. Oh
wow! So kilohertz IMU.
Yeah, kilohertz IMU, and then also microphone, and it's accelerometer, gyroscope, and then we also have a microphone on the back, time of flight sensor, and the camera. So 5 sensors in one.
And this is cool. You have an interchangeable lens here.
Yes, M8.
Lens. So being a computer vision person, the thing that drives me nuts is everyone thinks that they can grab a off-the-shelf camera that they use for Zoom and have good results on a lot of applications. And the reality is optics is a thing. Optics is a real important thing when building robotics, and you have to choose the right lens for the right application. And like these lens here, these tiny, like this is an M8.
Yeah.
These M8 lenses are fairly cost effective too, because if you're buying like a big CS mount lens or something like that, they're super expensive. These guys tend to be pretty cheap, and you get a lot of selection.
No,
so that's super cool.
And it has enough friction where you just set it to the right, and you just kind of turn it by hand, and it just stays in place. Best part about that though is it is matched. So that lens was the one the camera vendor recommended to us to the camera sensor, so you don't have any weird what are they called, chiffre angle issues and bad color problems. So we've done all of the camera qualification and actually lens shading. So it actually like really...
it's a good lens choice out of the box. But having the you see, I'm so small, I'm dropping it.
Yeah.
Having its postage stamp size here.
Yeah, and then also what we've got going on is USB high speed, USB-C. We have a quick connector for the SparkFun ecosystem, and that also can be connected to Adafruit's ST Emma, and then I guess you can also get into SparkFun's Grove connector too by using some add-ons. So easy way to interface with other logic. We also have I/O pins exposed on the side, so you can just solder directly to them. Yeah, just make it easy for you. Just 4 pins, but that there's also a JTAG connection on the side, so you can actually single-step the processor and do any fun debugging to edit the code. And then Wi-Fi Bluetooth built in.
Wow.
Yeah, a lot of packed into a small package. And then finally, on the back, there is a board-to-board connector. So you can actually stack boards and build more complex systems.
Oh, crap. I didn't even see that.
I know. It's so tiny, right?
Is this one of the ones that you can reuse a couple times? Because some of them are disposable.
Yeah, it's terrifying. It's a high-ros one. It's one of their DF series, so it's actually like decently quality.
High-ros makes good connectors.
Yeah. A little bit expensive, but it's worth it though, because we had one customer who bought some previous boards we designed about this size, and there were no board-to-board connectors, and so they were soldering shields on.
like 50 different wires coming through, or 24 wires.
We made a shield that plugged right into the back, and so you had to solder it still.
Oh, okay.
And it sounds not bad until you realize they actually were trying to do at-scale deployment, and so imagine you have 600 of these now.
So some poor tech is having to make 600 of these things.
Yeah, they had to actually bring in their kids and have a solder party.
This is one way to do it. The kids learned. Yeah. Jesus, these components, these are all like 01, 005s or something.
No, 0201s.
Oh, they're 0201s.
1 millimeter chips. I mean, you even have these are voltage. That's like a voltage regulator and a power switch, and it's that little 1 millimeter by 1 millimeter black rectangle. So really pushed it for this design. And then finally, the main event though is the chip in the center. That is the. This is the Aleph Ensemble. It is a new microcontroller. It features 2 processor cores with neural processing units on board. And so this guy has 200 gigaflops of neural network acceleration on one core and 46 gigaflops on the other core.
So one is basically your workhorse, and the other one's going to be tending everything else, kind of.
Well, the idea is that you can shut off the main core and then go into a low power mode. Where you're going to be at hopefully sub 10 milliamperes, and that'll let you do 46 gigaflops of neural network compute, which is far beyond the capability of any microcontroller before, but at almost no power draw.
So the use case here would be, I have a...
Well, like that work just happened.
Well, like a camera, like a game camera, right? Like a game camera basically spends 90, we have raccoons and stuff. I always kind of want to see them with a game camera. It spends 95% of its life, nothing's happening. It's just sitting there doing nothing. And then but like when it turns on, when you see something, when the animal walks up, you want to be able to do something, a high throughput task, right? You want to do a ton of processing.
And here's the nice thing about this, which is that because there's a microphone on board, you could, for example, listen to audio. And when you heard something approaching, you then turn on the camera before it comes into the field of view. That way you capture all the video. We've heard that be a problem some people, have dealt with, which is they want to capture the thing that actually they're supposed to capture, not after the fact. But so you have both the accelerometer, the gyroscope, and the microphone on the low power side that can be run when the thing's in low power mode. And then the high performance core can interface with the camera. And at 200 gigaflops, you have enough performance at that point to actually run an ML model at, you can run YOLO pretty much. A YOLO V5 Nano model, about 224 by 224, hits about 28 FPS. And if you want to use a small model, so Nano's about 2 to 3 megabytes, and then small would be about 8 to 10 megabytes. And so an 8 to 10 megabyte size one, that'll run about 10 FPS. But both of those frame rates are still quite usable for real applications. And a small model will have a lot better performance than the nano one for like bounding box quality and identification per se.
But basic object detection, right? You just really, a lot of times if you're trying to, so I can see one application would be, I have a gripper, you put two of these in the gripper, you're just trying to find the centroid of the thing you're picking up as you're approaching it, right? Yeah. And you just want the signal to come out of the box that says, in my field of view, it's right here, it's right here, it's right here. And that's, how you kind of build that application. That's cool.
Yeah. And so with this, you could actually then interface this with ROS. We do MicroPython on board by standard. That's the operating system.
Yeah.
So it's not going to be, day one, we got ROS support. But, as the community helps and builds out the software, we'll be able to integrate this with ROS and actually have the means to, make it so this can be an easy to use sensor for folks who want to actually add computer vision right to the edge, but not just computer vision, but actually decent high performance computer vision.
Well, the problem that people run into, right, is they try to cram too much on a Raspberry Pi too, right? So this is nice in that especially the lower end of the Raspberry Pi spectrum, right, is really, they're pretty slow devices, but this will, you take one of those and one of these, and you're kind of in a space where you can do some interesting stuff.
Well, here's the fun stuff. Here's the fun thing. When I mentioned that 204 gigaflops number, if you think about pegging a Raspberry Pi 5's processor at every core running SIMD operations at the max possible throughput, the neural network accelerator outperforms the entire processor with all cores pegged at 100% max. So having these accelerators makes a huge difference.
No, it absolutely does.
It's just
it's a little tiny GPU.
Yeah. No, it's if you don't have the acceleration, it doesn't matter how fast your CPU is. Once you have those neural processing units, they just totally beat anything previously. For example, with this little guy, we had the OpenMV Cam H7 kind of was our last solution, and so that performs at about that performs about 0.3 frames a second, and it can run YOLO at that speed, and it draws about 160, 180 milliamperes. So now we're running YOLO at 28 FPS, and we're drawing 60 milliamperes. So we've cut the power consumption by a third, and improved performance by about pretty much 100 times. So it's literally between 200 and 300 times faster than what we were previously doing. And it's just thanks to, I guess, the silicon industry and, putting these incredible chips out. Anyway.
I mean, you've been trying to get this chip up and running for a while. This is a brand new device as far as I'm aware.
Yeah. We've been working on this for over a year now. Lots of bottlenecks, problems, issues. The latest ARM standard has firewalls all over the chip, for example. So security, bus master control, different they just keep making it more and more complicated for how you talk to things. You have to set up certain memory protection units that specify the attributes of memory areas. And if you don't set those up correctly, hardware just immediately stops functioning and turns off because it violated some attribute that just because they want to make security really important. So I
mean, it's kind of important, but it's also a pain to set up, right? It's always a pain to set up.
Normally, though, it was you enabled it. This is always on. You have to explicitly
turn it off by default. This is good. But I also get that it's a total pain in the butt. Yeah. It's just oh God, another thing I have to do. I never used to have to do this.
Yeah. But this is, I think it's cool for the future though, because when we think about how this can connect with ROS, it really leads to a solution where we can really be combining and composing systems of different computers more easily. And that's what really big robots look like, right? I used to do self-driving trucks.
Yeah.
And those had multiple systems that were all networked together communicating.
Well, people are really desperate for, there are really good professional cameras, but they're really expensive. It takes weeks to get them. It's a whole process. And then there are, the things you use to do a Zoom call, or the things that, the cameras that you use to go take photos. But in between, in this space of I want something where I can build an application that's small, low cost, is able to actually do some processing on board. There really isn't that many games in town. And so this is really cool. Like, I remember when I've had to build stuff like this, you basically have to go through a professional camera vendor, and it takes forever. Like, it's expensive. Like, it's not like you can just plug the thing into USB and get a signal either. Like, it's a lot of development time, and it was never a good process, right? It was like, there's nothing in between where you can just grab a board and start working with it, change out the optics a little bit, and then build around it and have like a fairly open development experience too. That's the whole other side of things. You know, most of these professional cameras, they're emailing you a zip file with their source code or something. Some of them have gotten a little better in the past 5 years, but like a lot of them are emailing you a vendor and emailing you a zip file, and it's not a great development experience.
No, that's what I used to run into also. One of the things we wanted to do at OpenMV actually is that we put our source code online, and we also have every single one of our board designs is available for schematic review and PCB review online using Altium's 365 viewer. So you go to our website and you can actually see the schematic. You can click on a wire, and then the wire actually highlights on a PCB board if you go to the PCB tab, and you can instantly find where that wire is connected. And we find that useful because it's like, if you want to hack the system or figure out what's wrong or why it's not working, you can actually just do that and not send me an email and not ask for help support. We try to make it available.
Not have to log into the portal to download the specification to figure out what pin I can wire this up. Like, if I have to wire it into my robot to get power, like, I don't have to email you to get the spec to go and do the thing, which is like, I don't think most people understand that this is a thing that still goes on nowadays.
Well, this is the thing.
This is why things take forever.
It really is. When you're building like complicated robots using high-end parts, a lot of times you are you're having to interface to another company's help support that doesn't really want to give you the information you need. And so the speed at which you can do work really is dictated by how many emails they answer a day and how fast they get back to you. And that can be substantial sometimes. Like, sometimes it's at the speed of one question a day. And so, working through a complex problem then can take weeks, even though if you could just connect the two people together, they can just go at a high speed. But because we try to silo data in one place or another and prevent people from seeing things.
I mean, that's also why old people will tell you, just give them a call. Too. Because then you can ask all your questions at once. I know, I feel really old when I say this. Just give them a call.
Yeah. Well, that works as long as you're in the same time zone. Continent. I know. But sometimes when you're between continents, it's a real big problem.
Exactly. So this is cool. Wait, don't you have other boards too?
Yeah, we do have one more. So let me just show off that real quick. So we've actually got so this is
wow. You brought all the toys.
Yeah, I brought all the toys. So this is the OpenMV Cam N6.
Too.
Yeah, we actually got into 3D CAD design. We brought someone on board who's been really helpful on that.
Just to do enclosures and like mounting.
Yeah.
And, that's cool.
Yeah, I never had the ability to make a tripod mount.
So just go on Thingiverse and pull it down and print it.
Yeah, we put everything on GrabCAD. And so this makes everyone's life easier. Like, all the 3D files for all the boards are on GrabCAD along with the case design.
Nice.
And the OpenMV Cam AE3 will come with with an injection molded case, but the files will be available for download for you to 3D print your own. And then this actually snaps into things.
I mean, to be quite honest, right? Like, if you're a professional engineer, you're going in and you're like, okay, this is like this, sitting there with the calipers, it's this way. Or maybe if you're like, you have the spec sheet, right? But then you have to go CAD all that up and print it yourself.
Yeah,
and
we'll save you that time. Yeah.
And usually it's like the cherry on top. You're doing that in the afternoon after work.
Yeah. No, this we try to give you the files to download. I saw that a lot at the last robotics company I worked at, where the 3D engineer, the mechanical engineers, their lives are made so much easier when
just having like where the screws are and the standoffs are, so you can print it. Just start there, and you can mix CADing stuff up so much faster.
Oh yeah, no, we'll give you the whole design, so you actually just get an STL file that has the entire board of all the parts, pretty much accurate. And using that, then you can design anything you want, and so it just saves you hours and hours of work. And so what we got here, this is the OpenMV Cam N6. So AE3 is the little brother. Low power, fast, high performance. And then the N6 is based on the new STM32 N6 from ST Microelectronics. And so this one is like our traditional OpenMV Cam. So it's got replaceable lenses. You can swap out to put different things on board, and etc.
Lens modules, basically?
Yeah. So you got FLIR Lepton, a FLIR Boson, which is 60 hertz, 640 by 480 thermal camera. You've also got your OV5 640, 5 megapixel rolling shutter, and then we'll have the same 1 megapixel global shutter color camera for the STM32 N6.
You want the global shutter.
Yeah,
Trust me, you want the global shutter every single time.
But we'll also have a HDR 5 megapixel rolling shutter camera too. So you'll have that also. So if
you're doing outdoor applications or something.
Yeah, we want to make sure we cover that. So you'll have camera sensor for any type of thing you want to do, and also there's one more camera sensor called the Gen X320, which is an event camera from Prophecy. And so this lets you see just differences and pixel changes. So the advanced cameras are
they're the bleeding edge right now. They're really pretty cool. I think I've seen one ROS package for them so far. There's a lot of research going on. What's interesting about it is, like, if you're doing 3D reconstruction, there's this thought that the event cameras where so the camera basically only sees, if you want to think about what it sees high frequency, sees edges at a very high frequency.
It's just like different image differencing.
Yeah, it's image differencing, but super duper fast. And so those edges, the two edges going perpendicular to each other, right, create a point, and those points are basically what you use as your feature points when you do 3D reconstruction. So there's a thought that you could do way faster, way better 3D reconstruction using event cameras. At least that's the hype, the thought.
Yeah.
So it might be really cool stuff.
Yeah, so we have that also with the OpenMV Cam. It's a lot of different camera sensors. And this board is like the AE3, same software environment, by the way. You got USB high speed, you've got the main processor, you've got the camera interface, which is MIPI CSI or 8-bit parallel.
And this thing is like the perfect size for a drone too, right?
Yeah,
weight-wise, and, well, both of them are. The other one's smaller, but this one...
Yeah, this is the base board. Also, accelerometer gyroscope located right behind the camera, microphone on board. You have an SD card now, and so the SD card can run at 104 megabytes a second, so you actually have like high throughput SD card.
So you can, if you want to, you could do a quick dump to an SD card.
Yep. Gigabit Ethernet on board, so not just 10, 100, and 1,000. So it can actually straight up interface with a ROS system, and you can be pushing some packets. You can also, it also has Wi-Fi and Bluetooth. Yeah, Wi-Fi, Bluetooth, and then also it has 64 megabytes of RAM at 800 megabytes a second. This is a microcontroller, by the way, not a Linux processor. It's bare metal, so you have bare metal 800 megabytes a second RAM to play with, and also 400 megabytes a second OctoSpy flash to play with, 32 megabytes of that. But the real key is the main processor. So the main processor is a 800 megahertz Cortex M55 vector processor. So that means it does 16 operations per clock. So way faster than a normal microcontroller, plus the higher clock speed. And then the biggest piece, though, is it's got a...
It's faster than the computer I took to college.
Yes. Yeah, this thing has the specs to run Windows XP now.
Yeah, I was going to say, you could run Windows, you could legitimately...
It actually beats my Windows 98, what is it? I was playing StarCraft.
You could play StarCraft on it.
Yeah, this thing can play StarCraft, most likely. But here's the best part. It's got an ISP, an image signal processor, to receive camera data. So all of the operations to take in a raw Bayer image and translate that into an actual usable image, it's got that in hardware. It's also got an MPU, so 600 gigaflops MPU, so 3x faster than the smaller camera. And finally, it brings in a H.264 hardware encoder. So it can actually record high-quality video content now, and JPEG too. So it's really like, this thing has everything you need to be a compute powerhouse, and give you a microcontroller that can basically replace an IP camera, but now it's got an IP camera with ML on board. You can be at your end-effect grippers, I mentioned. We have a...
Well, yeah, it's an IP camera that you can actually go and figure out what you want on there instead of relying on, just using it as like a source of imagery, right? And you can actually run a few useful things on there, and
you have no idea.
And output signal, right?
You have no idea. Like, doing robotics, I know how many IP cameras end up getting integrated into ROS. With you use like RTSP protocol, and you pipe that over OpenMV or FFmpeg, and then you can make a ROS node to get video data in.
Yeah, or people use them for external monitors too. And a number of times I've used one like, somebody's got to watch the robot while it does something because we want to catch it breaking. It's the other case where I see people using IP cameras. It's like, oh, we need who watches the watchers?
Well, the thing about that is it's just like every IP camera is not designed to be automated in its bring up. It's always like the technician has to actually like go into a web interface and type a bunch of stuff, and it's like none of it can be automated of a script that just says plug it in, load program. None of it's like that. It has to be, you know, a setup procedure they have to follow. And it's funny that, because they're not meant for this. There's always the problems that we're reusing IP cams in a way.
No. People are always, and that's the problem, is that people are hacking web cameras, hacking IP cameras. Like,
yeah.
And hacking's not even the right word. You're trying to put a square hole or a square peg into a round hole, and like you really should use a decent tool like this for the job. Yeah.
So before we go, I mean, just what do you think we could do with this kind of technology? What could we bring to the ROS community?
Well, the first one is, there's the set of, God, there's tons of things, right? So the first one is there's just lots of people trying to build their first robot, trying to build little tiny, I want to build my first robot. I want to build something like a Turtlebot or a smaller version of Turtlebot. This is a good choice because usually you're super cost sensitive, right? But you want some power to play with and something that you can do different projects with. So that's a great one. There's the whole, sort of teaching foundation model, Aloha stuff going on right now, right? The hope. And there's been some progress, right? As you put the camera on the end effector, you have a secondary controller, you do a task, you teach the robot collects some data. This would be great for that. There's just the general end effector. We put the camera at the end of the end effector for the robot, and I can help line stuff up, do some tasks. So all of those are good. The one that I know I've said this probably 5 times to you in the past, but still really excited. Somebody really, really needs to make a mocap system out of these. What I want is the sub $500 mocap system where I put 5 of these in my living room and I can get position data, because I think it would be super cool to have a cheap and low cost system for tracking robots, for doing dynamics testing. Yeah, I mean, just generally, all robots need to have some sort of camera. And if not for planning or path planning, you need something just for like teleop, right? Most robots are not, despite people's claims, most robots aren't completely autonomous all the time, and you need a camera just to be able to go look around, capture some data, and do some stuff. But it really, there's a ton of applications. It's gonna boil down to what you want to do. The feature for the Lepton is also really nice.
Yeah, well, that's for the industrial customers, because they've actually asked for high performance thermal.
Really, for quality assurance or for?
Well, it's actually like crazy stuff. Like, imagine you're an industrial customer and you want to check to see the bearings of like a motor about to burn out. It turns out you could try to do like frequency analysis, or you can try to do vibration analysis, and those also work. Or you could just point a camera at it and see what the temperature of the bearings are, and it pretty much directly correlates with that's about to to catch fire.
Well, yeah,
catch fire and break, basically.
Yeah, this is you and I have had this conversation. The number of, like, whenever you write a computer vision library or sell a camera, the number of people who just like want a cheap camera and a cheap computer to point at like a dial from like 1950 or a piece of hardware that they just want to have remote monitoring for it's kind of crazy.
Yeah, no, it's there's a lot of applications like that, and thermal, definitely making that more accessible is something that really helps for people. And then we're also going to be excited to see what people do with the event camera support, as we're one of the first companies to make this available at a low price.
This thing has enough horsepower. You could do some. All right, the thing I want to see from people is like event camera slam on board this thing, because I think you could probably do it.
Oh yeah, you can, especially with the GPU, especially with the MPU. We definitely have enough horsepower on board.
Interesting.
Yeah.
Or 3D reconstruction too, depending on the surface. That would be really cool. You just have a little box you wave around, and out comes like an STL file.
Yeah, that'd be nice. We'll see what people do with it. We're excited to get the tech out. Anyway.
Yeah, cool.
No, thanks for making time to talk to me today. I appreciate it. Don't want to have this interview go on forever. Got to give people some of their time back. But any closing thoughts, Kat?
So I will say this. I remember buying the first one of these, like version 1. And then and like you're just like, there's more product lines, more cool things. Like it keeps scratching all the itches, which is really cool to see.
Thank you. Yeah, no, Kat's been a supporter since day one. We were shipping liquid garbage back then, but
liquid garbage. It wasn't that bad.
It was, how do you say if you're not ashamed of what you launched with, you launched too late?
Well, yeah, but it was also in a lot of ways better than the thing. All of those problems that I've complained about still exist, and you're still trying to fight against them, which I think is really important.
Thank you. Thank you. All right, everybody. Thanks for watching.
Bye-bye. Cool. All right, now I'm really curious. Was that a real legit earthquake?